In the video here and in the next two after this, we're going to be looking at elimination reactions. This is where we form an alkene group from a compound that doesn't have any sp2 carbons where the alkene is. Okay? All right. So the first reaction we're going to look at is called dehydration. Okay? In the dehydration reaction, we are going to be taking an alcohol, like you see in the upper left here, and we're going to define carbons here by this unofficial nomenclature system called the alpha-beta system. And alpha is merely defined as the carbon of interest. Okay. And obviously that can't be a IUPAC term, right? Because that's what's interesting is in the eye of the beholder. Okay? All right, so if you look at this particular molecule in the upper left, you'd probably say that the most interesting carbon is this one, the alcohol-bearing carbon, or the oxygen-bearing carbon. And we're going to call that one alpha, and we're going to call the one next to it beta if any carbons further down the chain became interesting to us. We would give them successive Greek letters like gamma and delta. Okay? And what happens in the dehydration reaction is that we make water. We take an alcohol and we eliminate water from it. Now, how do we make water? Well, we're going to take the OH off of the alpha carbon and a hydrogen off of the beta carbon. These two are going to come together, and that's where our water comes from. Okay? In the process, both the alpha and beta carbons, they have one less thing on them, so they're going to now acquire a double bond between alpha and beta, and this is where the alkene group comes from. Okay? So the alpha and beta carbons become alkene carbons. Okay, this reaction requires an acid catalyst. What we need is a little bit of acid. We don't need a 1 mole to convert 1 mole of alcohol to 1 mole of alkene. And we'll look, when we look at the mechanism, we'll see why that's the case. All right, alternatively, we can form an alkene from an alkyl halide. And this process down here at the bottom is known as dehydrohalogenation. We're going to designate the alpha carbon as the carbon that has a halogen on it and the beta carbon as the carbon next to it. What we're doing here is we're ripping HX out of the molecule. Okay, and to do this, we're going to need base, and we're going to need 1 mole of base. Okay, so what we're doing is we're taking the molecules of HX, which you remember correspond to a strong acid. Okay, and the X comes off the alpha carbon, the H comes off the beta carbon. The two carbons that we've designated alpha and beta become an alkene as a result of this process. Our halogen here has to be chlorine, bromine, or iodine. Fluorine, the CF bond is too strong, and it's not actually all that good of a leaving group either. Okay, our base here, since it's removing HX, it's actually going to neutralize it. So our byproducts here, let's pretend the base has a negative charge, it's going to just be the protonated base and the halide anion. If we had a counter ion like sodium hydroxide, we would not show it as being X minus, but just NaX or whatever. Okay? All right. So we're going to look at the dehydration first. And let's look at it in some level of detail. Okay, so here are some sample equations for dehydration. Notice that the acids are different. The top one uses sulfuric acid and heat. That is the most common reagent system that you see employed for this transformation. Some other acids that often are used are the conjugate base or monoconjugate base of sulfuric acid, sodium bisulfate, which is shown in the second equation, and phosphoric acid, which is shown in the third equation. All right, so the simple system involving cyclohexanol is going to make cyclohexene, as you see here. Okay. Now this is a totally symmetrical compound, so there are no complications. But let's look at this compound here, this non-cyclic compound. I'm going to designate that as the alpha carbon. And if I designate beta carbons, you can see that I can designate two different carbons as being my beta carbon. Okay? So we're going to have beta carbon that I just called beta, and then I'll call it beta prime. Okay. All right, so when we do this reaction, and by the way, it's not really reagent specific. Pretty much any acid reagent is going to produce a similar ratio of compounds. All right, the major product here tends to be 2-hexene, shown here. It's obtained as a mixture of cis and trans, slightly favoring the trans, but as we'll see in a second, that tends to be the general trend, that the more stable compound is produced here. And as a minor compound, you get 1-hexene. Okay, so this is a minor compound here, 1-hexene. All right, when we look at this other compound, I'll just give them, since we have a lot of betas, beta 1, beta 2, and beta 3, and beta 2 equals beta 3. What we find here is that our elimination reaction produces predominantly the products from taking a hydrogen off of beta 2 or beta 3. And our major product is this alkene, the tri-substituted alkene. The disubstituted alkene is only a minor product. And this type of alkene that's outside, or has one carbon in a ring and one carbon outside a ring, we tend to refer to as an exocyclic alkene. Okay, what you see here in these last two examples is a trend that is starting to emerge, and that's that this dehydration process has produced the most stable alkene in every case. Okay? All right, so this alkene here is more substituted. Okay, it's 1,2 disubstituted, and this one is monosubstituted or less substituted. Of the disubstituted alkene that you see more trans than cis. Okay, so what we see here is that the alkene prefers to locate itself in the more substituted position, the 2 position over the 1 position, or the middle of the chain over the end of the chain, and it prefers the trans isomer over the cis. And we've realized that this is totally paralleling alkene stability, right? The more substituted alkene is the more stable one, and trans is more stable than cis. In this third example, the same thing is emerging. This alkene here is tri-substituted, and this alkene here is disubstituted. Okay, so we've, in every case here where we have multiple alkenes that could form, we form the more substituted one. This is called Zaitsev's rule. And Zaitsev's rule basically says that dehydration is going to produce the most stable alkene. Right now, the primary property that's affecting alkene stability is the degree of alkyl substitution. Okay, so right now, until we introduce some more factors, we can say that the more substituted alkene is going to form as a result of the dehydration. Another way to say more substituted is to say we're going to obtain the alkene that has the fewest hydrogens directly attached. Okay, Let's predict the products of this reaction here. All right, so we're going to want to have the alpha carbon as part of our alkene, and one of the beta carbons is going to be one of our alkene carbons. So in this case, we're going to do our dehydration, and our major product should be this one, okay? And this is from removing a hydrogen at beta 2, or at beta 1, okay? If we remove a hydrogen from beta 2, we would get this compound here as a mixture of cis and trans, and this we're not going to obtain. This is only going to be its minor because it's less substituted, okay? The red alkene is a 1,2 disubstituted alkene. The blue alkene that I've designated as the product is a tri-substituted alkene. If you count the number of hydrogens on it, you can still see that it's the fewest hydrogens on the alkene. There's 2 alkene hydrogens here. There's 1 alkene hydrogen right there. All right, same analysis is going to occur here. That's going to be alpha. I'll call it beta 1, beta 2, beta 3. Let's make a better 2 there. And what you see here is that beta 1 doesn't have any hydrogens on it, so we can't form an alkene there. We're going to form our alkene by pulling hydrogens off of beta 2 or beta 3, and beta 2 is the better place to do that because this produces the tri-substituted alkene that you see here. It's not going to remove the hydrogen from beta 3. Because this alkene is only disubstituted, and this one is tri-substituted. Okay, the last one, we have a red herring here, or a functional group that's not going to do anything, and that's the chlorine. The acid catalyzed dehydration is specifically a reaction of alcohols. Okay, so we have alpha, beta 1 and beta 2, and we're going to remove the hydrogens exclusively from the beta 2 carbon because that is going to produce our more substituted alkene. The chlorine is just going along for the ride in this particular reaction. If we had removed a hydrogen from beta 1, we would have gotten this, and that would be only a monosubstituted alkene, and this is a disubstituted alkene. So we would prefer to form the alkene to the right, okay, or the blue alkene over the one that I've shown there in red. Okay, all right. So let's look at the mechanism for alcohol dehydration. First, a couple of facts. It's well known that tertiary alcohols react much faster in this reaction than secondary, much faster than primary, and that the rate is it's a first order reaction. The rate only has the alcohol or the protonated alcohol as in the rate equation, not the halide, not the anion of the acid, okay, or not the acid. The acid doesn't really enter into the rate equation. Okay, you also probably notice here that I show here that dehydration is a reversible reaction. In theory it is, but the reaction going to the right is a little bit easier to do. What we're going to see in the next chapter is that we can also add water to alkenes, and we're going to discuss that to some extent, and we'll see there that the reverse of this reaction isn't necessarily the best way to do it, but the reaction going to the right is dehydration, and the reaction going to the left is acid catalyzed dehydration. Okay. What you also find is that when people do this reaction, they actually use Le Chatelier's principle without really even knowing it. Water usually boils lower than most of the alkenes that you would make, and a lot of times it just goes out of the system. Okay, so that's one way to drive the reaction to the right using Le Chatelier's principle. Another issue is that sulfuric acid has a tremendous heat of hydration. Okay, so when you add water to sulfuric acid, you might notice that it gets hot, and so it's very exothermic to actually pull water out of this. It tends to hydrate the sulfuric acid. Okay, all right. So we've seen this relative rate before with alcohols in the previous chapter when we look at their reaction with HCl, HBr, and HI to make the corresponding alkyl halides. Okay, and this reaction has a great deal in common with that reaction in that it involves carbocation intermediates. Okay, now what we'll see here is that the mechanism looks remarkably like that mechanism, except that we're using a different acid. In the first step, since sulfuric acid is a strong acid, this reaction is going to go to the right. And in the first step, we just take the alcohol, the acid, and form the protonated alcohol and the anion, or the conjugate base of the acid. Okay, this is just, as we stated before, the Bronsted-Lowry equation where water has been replaced with an alcohol. Okay, in step 2, we are going to remove water to form a carbocation, and this, like it was before, is our rate determining step. This is the least favorable step. This is the step where you have everything coordinatively saturated, or everything has an octet on the left side of the equation, but when you do the dissociation of water, you of course form a carbocation which only has 6 electrons at the carbon that we give a positive charge to. Okay, so that's our slow step. That's the least favorable step, and we can sort of use this step to rationalize the relative rate. Okay, tertiary alcohols react the fastest because tertiary alcohols afford tertiary carbocations. Okay, and tertiary carbocations are the best carbocations of them all. All right. Now, once we form this carbocation, we're going to remove a hydrogen from the beta carbon in the very last step of the reaction. Okay. Sulfuric acid, it turns out, is a stronger acid than HCl and HBr, and as a result, its conjugate base is a lot less nucleophilic. Okay, so the preferred process at this point is not adding the bisulfite anion to the carbocation, but rather removal of a hydrogen from the beta carbon using this set of arrows right here. Okay, so we're going to take water or the bisulfate anion. It's going to remove a hydrogen, and as the hydrogen is removed, a double bond is formed, and this gives us the alkene. Okay, step 3 is a very favorable, very fast step, and this is fast because we're taking the only intermediate that doesn't have an octet and giving it an octet by making the alkene. Okay, in the next cycle, we're not necessarily using sulfuric acid. We might be using H3O+. So imagine that if we had H3O+, we could use a similar set of arrows to protonate our compound as well. So right there in the second cycle, it could be H2SO4 or it could be H3O+. Okay, either one could initiate the second cycle. And this is why the reaction is, in theory, catalytic in sulfuric acid. It turns out that because sulfuric acid becomes a weaker acid in the presence of water due to the hydration process, people often do use more sulfuric acid than is truly a catalytic process. But if you get rid of the water as it forms by boiling it out of the system, you can use sulfuric acid catalytically. Okay, all right. I think this is where, now we have one more problem, don't we? No, this is where this video is going to end. We're going to, in the next video, look at a little complication that can happen, particularly when we have secondary and possibly primary carbocations involved in our elimination reaction.